Loop analysis is a different technique for solving or calculating the parameters inside a circuit, either it is current or voltages. Okay, but now we use Kirchhoff voltage law, KVL, instead of Kirchhoff current law. In Kirchhoff current law, you use the law that current, the sum of all current entering into the node should be zero, or the sum of current entering or flowing out of the node should be zero. Or in the third expression, the current flowing into the node should be the same as the sum of the current flowing out from the node. Okay, that is Kirchhoff current law. In Kirchhoff voltage law, the voltage, the sum of the voltage in a loop should be zero. Yeah, so the addition, the plus minus, all when it is added inside a loop should be zero. So this is what we are going to use or to learn in this subchapter. In later in any analysis in the later chapters, in the next chapter, you can choose whether you want to use loop analysis or you want to use nodal analysis, as you like. The result should be the same, only depending on the drawing on the circuit diagram. Then we should have, if we do a lot of exercise, we will have some intuition which law is easier to implement, yeah, for particular circuit. So loop analysis is a second systematic technique to determine all currents and voltages in a circuit. It is dual or complementary to node analysis. So it first determines all current in a circuit, yeah, in loop analysis, and then it uses Ohm's law to compute the necessary voltages. So this is in opposite to node analysis. In node analysis, you are using Kirchhoff current law to determine the node voltages, right? The voltages at the node. After which, then you can calculate the current in any branch using Ohm's law. In loop analysis, you determine first the current flowing in the loop, yeah, in any branch. After that, then you can calculate the voltage using also Ohm's law. There are situations where node analysis is not an efficient technique and where the number of equations required by this new method is significantly smaller. So, as I mentioned earlier, which one to apply, yeah, in practical or in later circuit analysis depends on the situation of the circuit. And the easiest will be if the number of the required equation is the fewer. Yeah, the fewer the number of equation required to solve a circuit, then it means that method is simpler. Okay, so let's consider this circuit having three resistors R1, R2, and R3. Is this a single loop? A single loop circuit, and having two sources, 12 volt and 18 volt, and apply node analysis to this circuit. So here you have 4 non-reference nodes. Yeah, here how many? 4 non-reference nodes. Let's say if we take this as the reference. For example, we take this as the reference, then we have 1, we have here 2, we have here 3, and 4. 4 non-reference nodes. It means we have to write 4 KCL equations. Okay, so yeah, here 0, V1, V2, V3, and V4. And there is one super node here. You can take this V3 and V4 as one single super node. Okay. So then there is one node connected to the reference node through this voltage source, which is V1. Okay. So then you need 3 equations to compute all the node voltages, V1, V2, V3, and V4. But actually there is only one current, right? You have four unknown, but there is one super node, so you can simplify it into 3 equations. If you use node analysis, you use Kirchhoff current law. But if you use from different perspective, if you use a current, because this is basically a single loop, there's only one current flowing through all the components. And if that current is determined, if we know that current, then we can easily determine all the voltages between or across the resistors using Ohm's law, right? This is one single loop. So let's then apply Kirchhoff voltage law, which states that the sum of the voltage drop across a single loop should be 0, or the sum of the voltage increase should be 0, or in different words, in the third expression, the sum of the voltage drop should equal to the sum of the voltage increase. Yeah, so here, if we take it as voltage drop from this node to this V1, from the reference to V1, yeah, the voltage drop is negative, right? Because it is positive, it is a voltage increase. So if you look from the perspective of voltage drop, then it is negative 12 volt. So plus VR1, because it is voltage drop across VR1, plus VR2, voltage drop across resistor 2, then plus 18 volt, yeah, because it is another voltage drop across this independent 18 volt voltage source. Then negative VR3, because here VR3 is drawn as with this node is higher than this node, the right node. So from, if we look the node from here, clockwise loop, then it is negative. The voltage drop across this R3 is negative VR3, equals to 0. Okay, then you use Ohm's law to express voltages in terms of this loop current. Okay, and so this VR1, you express it in using Ohm's law. Instead of VR1, you use I, the current, multiplied to R1, or R1 multiplied by I. VR2 is R2 multiplied to the current I. VR3 is I, or multiplied to R3. Okay, now be careful. So this is using the passive sign convention, which current should flow from flow into the positive polarity, then going out from the negative polarity, right? So in the R1, the sign of the current is positive. In the R2, the sign of the current is also positive. But in the R3, it goes from the negative polarity, right? Goes inside the resistor through the negative polarity first. So the sign of the current is negative. So that is why this here plus R3 I. Result in is one equation in the loop current. So if using Kirchhoff current law, using nodal analysis, you need 3 equations to compute all the node voltages. Using Kirchhoff voltage law, using loop analysis, you only need this single equation where you can find then the current I. After you find the current, then you can calculate the voltage VR1, VR2, VR3. Okay, so this is a shortcut. Yeah. So you can skip this equation and immediately write into this one directly. Okay, so this is some definition. Let's see. There are what we call as loops, then mesh, and loop currents. Okay, so each component is characterized in this circuit by its voltage across and its current through. Voltage across, current through. Okay, so this is component 1, component 2. It could be, the component could be a resistor, a load, could be a voltage source, could be a current source, could be also dependent sources as well. 3, 4, 5, 6. The node is A, B, C, D, E, F. Yeah. So a loop is a closed path that does not give twice over any node. So in this case, again, a loop is a closed path that does not go twice over any node. So this circuit has 3 loops. This is the first loop. Okay. F, A, B, E, F. Okay. F, A, B, E, F. So it only goes one time in a single node. In A only one time, B one time, E one time. F is only one time, but since it's basically the beginning and also the end, then we write it twice here. Second loop, E, B, C, D, E. Okay, so any node is only pass one time. The third loop is this one, F, F, A, B, C, D, E, F. Yeah, this is the third loop, the red one. Okay. So a mesh is a specific kind of loop where it does not enclose any other loop. So in this particular case, then F, A, B, E, F, and E, B, C, D, E can be called as mesh. So depending, you can call loop analysis also as mesh analysis if we do not use any loop which enclose some smaller loop inside, right? This F, A, B, C, D, E, F. This is a larger loop, yeah, enclosing basically two small loops inside it. So if you use only F, A, B, E, F, and E, B, C, D, E in this analysis, then we call it as mesh analysis. A particular sub branch of loop analysis which only use loop that does not enclose any other loop, the mesh. A loop current, yeah, so be careful here, is a fictitious or fictitious, according to this here. Later I will check whether this English word is correct or not. Fictitious current that is assumed to flow around a loop. So a loop current is not necessarily the real current flowing through any component. Later we need to calculate again. Especially this is true when there are more than one loop. And for example, there is a single component here, for example, here 7, that is basically passed by currents by two loops. The first FABEF loop and the second one EBCDE loop. So later, the actual current flowing through component 7 needs to be calculated from these two loop current. So the loop current is used during the analysis of loop analysis. And later for the actual current, we may need to calculate again, yeah, especially for components that is intersected by two or more loop currents. So again, a loop current is a fictitious current that is assumed to flow around a loop. Later, the actual current will be calculated from this loop current. So in this case, I1, I2, and I3 are loop currents. So I1 is the current flowing through this FABEF loop. I2 is the current flowing through the EBCDE loop, and I3 is the loop current flowing through the FABCDEF loop. So a mesh current is a loop current associated to a mesh. So in this case, it will be I1 and I2. They are the mesh currents flowing through FABEF and EBCDE meshes, respectively. So in a circuit, the current through any component, here I just mentioned, right? The actual current through any component can be expressed in terms of the loop current. Need to be calculated from this loop current. So these loop currents, they are not necessarily the actual current through the component. If the circuit contains only a single loop, simple circuit like the previous slide, then yes, that loop current will be immediately that current flowing through that all the components inside that single loop. But if it contains more than one loops, like this circuit, for example, then we may need to calculate the current through any component expressed or from these different loop currents. So an example here, IAF, the current flowing from A to F here will be equals to negative I1 minus I3. So IAF here. IBE, the current flowing, yeah, because here you see that IAF, let me annotate here. IAF is this current, right? IAF is this current. IAF. And how many loop currents are there here? There are two, right? There are two loop currents flowing through AF. The first current is I1, flowing this one from F to A. So when when IAF is from A to F, then it's supposed to be negative, right? This is where it comes, because it is opposite to the direction of I1. Then the second current flowing through A and F is I3, right? I3 also flows from F to A. So then here we also have to put negative sign here. So IAF equals to minus I1 minus I3. What if instead we express it as IFA? Then in that case, we calculate it from I1 plus I3. Second is IBE, so from B to E. So here from I1, the contribution from I1 is positive because I1 also flows from B to E, right? In the loop FABEF. The contribution to IBE from I2 will be negative because I2 flows from E, B, C, D, E. That's why here IBE equals to I1 minus I2. BC here contains two contribution from I2 and I3, and both has positive direction from B to E. That's why IBC equals to I2 plus I3. Okay, clear so far, I hope. Okay, so let's see here. Save first. Clear drawing. The fact not every loop current is required to compute all the currents through the component. So basically, even from here, we do not really need I3. Yeah, we can use only two loops, FABEF and EBCDE, using only the mesh current. Okay, so we only need I1, and maybe we can use I3 here. Either we use using two loops current, I1 and I3. We can already calculate all the currents flowing through component 1, 2, 3, 4, 5, 6. So IAF, as similar as previously, can be calculated from minus I1 minus I3. IBE here can be calculated from I1 here. IBC can be calculated from, IBE, yes, can be calculated from I1 only, while IBC can be calculated only from I3. So you don't need really to use I2. For every circuit, there is a minimum number of loop currents that are necessary to compute every current in that circuit. So such collection is called as minimal set of the loop current. So similar like the KCL, right? In the node analysis, there is a minimal voltages that we need to know, we need to calculate in order to calculate all the every node voltages in the circuit. So for a given current, for a given circuit, for example, if B is the number of the branches, N is the number of nodes, then the minimum required number of the loop current can be calculated by L equals to B minus, in parentheses, N minus 1, or L equal to B minus N plus 1. Okay, the branches minus the number of branches minus the number of nodes plus 1. So mesh currents are always independent. So the mesh current, because they do not enclose any other loop, so they do not interfere with each other. Let's give an example. Here we have this circuit with R1, R2, R3, R4, and R5, and two independent voltage sources, VS1 and VS2. And here we draw two loops, or basically this becomes also two meshes, yeah, I1 and I2. How many branches are there? One, let's see here. So this one branch, the first one, 1, 2, 3, 4, 5, 6, 7. So 7 branches. How many nodes? 1, 2, 3, 4, 5, 6. 6 nodes. So the number of loop we require is 7 minus 5, or 2 loops. We only need 2 loops in order to be able to calculate all the currents inside that circuit. And from there, we can calculate all the other voltages in that circuit. So 2 loop currents are required. The currents shown here are the mesh current. yeah, because they do not intersect with they do not enclose each other. Hence, they are independent and form a minimal set of equation. The KVL on the left mesh is I1. So departing from F towards A, okay, is negative Vs1, right? Because the voltage drop is negative, because it is a voltage increase. Plus, sorry, from A, yeah, not from F. From A to B is R1. So this is supposed to be positive, yeah? V positive V1 plus positive V3 plus positive V2 here, negative Vs1. Negative Vs1 here. So from here, from A, B, E, F, A. Yeah, just look at A. Oops. So this is from A, B, E, F, back to A. Okay. Then KVL on the right mesh. So this will be Vs2. So B, C, D, E, back to B. Okay. So from B to C, voltage positive voltage drop. Okay, Vs2. C to D, positive voltage drop. V4. From D to E, positive voltage drop. V5 plus V5. From E to B is negative voltage drop because it is a voltage increase. So negative V3 equals to 0. Then using Ohm's law, V1, you replace the voltage in the loop equation with the current, the loop current, multiplied to the resistor. So V1 is replaced with I1 R1, V2 is replaced here with I2 R2, and V3 is replaced with I1 minus I2 R3. Yeah, remember, because in resistor 3 in here flows two loop currents, I1 from B to E and I2 from E to B. So the resulting current flowing through R3 will be I1 minus I2, right? I1 minus I2 multiplied to R3. V4 equals to I2 R4 and V5 equals to I2 R5. So by replacing and arranging these two equations, yeah, so now you group according to the current. In the Kirchhoff current law, you group according to voltage, right? V1 node voltage. In this loop analysis, you regroup it according to the loop currents. So from here, you group it I1, then inside parenthesis here is I1, yeah, multiplied to inside parenthesis R1 plus R2 plus R3 minus I. This Vs1 will be go to the other side of the equation, and plus negative I2 is because in I2 in R3 here V3 is equals to I1 minus I2 multiplied by R3. Okay, so negative I2 multiplied to R3 here, from this term. Then the second equation here, Vs2 move to the right hand side of the equation, it becomes negative Vs2, and the left hand side equation you group according to I1 and I2. So this becomes negative I1, yeah, because this V3 become is equal negative V3 equal. Let me write here. So this terms becomes negative I1 minus I2 R3, right? So that's why here then it becomes negative I1 R3, so positive minus times minus becomes positive I2 R3 this term. Okay. Then plus R5 for the V4 and V5 equals to negative Vs2. So then you can write these two equations as matrix form, remember. So I1 and I2 becomes the variable here, I1 and I2, and the first row and the first column comes from here, R1 plus R2, R3. The first row, second column from here, minus R3. Second row, first column from here, negative R3, because this is multiplied to I1. And the second column, second row, second column is from here, R3 plus R4 plus R5, yeah, multiplied by I2. Then this one. So this one, it can be easily solved using Octave or MATLAB, yeah, by inverse operation of the matrix, as taught before in the previous session. Not today's session, but 3 weeks ago. So these are the loop equation for that circuit. Okay. Okay. So first, let's see. Let's save this first. So an example. Let's have some example how to write the mesh equation. So we have here a circuit, yeah, having two mesh basically. Three independent voltage source, VS1, VS2, and VS3. How many branches are there? 1, 2, 3, 4, 5, 6, 7, and 8. So these are considered individual branches. So we have 8 branches. How many nodes? 1, 2, 3, 4, 5, 6, 7. 7 nodes. So then the required loop will be 8 minus 7 plus 1, right? Or equals to 2 loops. 2 loops current are needed if we want to know the voltages and the current flowing through each of the components, and then we can calculate the voltages accordingly. And we are told to use mesh currents. This defines the loop. Yeah, because here the problems state that the mesh equation that is easier, and you need only to use a loop that does not enclose other loop here inside this mesh. Identify all the voltage drop, yeah, the R1 here. So how to write, if you ask how to write which one is positive and negative, so yeah, at the beginning you can identify them, you can write it arbitrarily, but later, as if you know then that the result is negative, that you know that the polarity should be reversed. Yeah. So for example here, but to be easy, you use passive sign convention. For example, for R1, the I1 should enter the component from the positive polarity pole, right? So for positive polarity terminal, so you assign positive to this left part of R1 and negative to the right part. Similar with this I2, the second loop, second mesh current. So you assign here positive for R5, negative here. For example, here we may assign differently. So for example, here instead, then we assign negative. The current flows into the negative terminal of R4, going out from the positive terminal of R4. Similarly with R3. It doesn't matter actually. But later when we find it negative, then we know that the current should flow in a different direction. Then we write the Kirchhoff voltage law for each of the mesh. So at the top mesh, here negative voltage drop minus VS1. Yeah. So then flowing through the R1, positive voltage drop, positive VR1 here. Then flowing through the voltage source VS2, this is a voltage increase, so basically a negative, but a minus voltage drop, so minus VS2. Then flowing through the R2, this is a positive voltage drop, so plus VR2. The bottom mesh, we depart from this part, this node. So from here to here, it's negative VR2, yeah, because this is voltage increase, so negative VR2. Then here is positive voltage drop plus VR5. Here this is negative, then we assign, because this goes to the negative terminal, so negative VR4. This is a positive voltage drop. The voltage drops, yeah, because this is higher voltage compared to here. Plus VS3. So from here, this is a voltage increase. So it means from the perspective of voltage drop, it is a negative voltage drop. Negative VR3 equals to 0. Then we use Ohm's law, we replace VR1 by using loop current I1. Yes, then VR2 by using the loop currents that flows through R2, which is I1 negative I2, right? And similarly also with the second equation. Okay, so VR1 equals to I1 R1, VR2 here, yeah, equals to VR2 is measured from this relative to this. So here the current flowing through into this terminal is I1, right? I1 negative I2 because I2 direction is opposite to I1. VR5 is expressed as I2 times R5, and R4 here is expressed as VR4. Yeah, the voltage across R4 is expressed as negative I2 times R4. Why is that? Because here we express VR, the current is not, it's opposite to the passive sign convention. The current flows into the negative terminal, and not positive terminal. That's why we assign here negative I2 R4. Then similarly with VR3, current flows from the negative part, so we assign VR3 equals to negative I2 R3. So when then we replace this, so this one become minus Vs1 plus I1 R1 negative Vs2 from here, plus VR2 is I1 negative I2 times R2 equal to 0. So here then VR2 we replace here with we this one we put this one first, yeah, negative VR3. So negative times negative become positive, right? Positive I2 R3. Then at VR2 is here is negative, so negative I1 minus I2, so this becomes I2 minus I1 multiplied by R2. Then at R5 is here, so plus I2 R5, yeah, positive, so this is also positive. Then at R4, negative R4, negative VR4, negative times this negative I2 times R4, so becomes positive I2 times R4 plus Vs3 equals to 0. Okay, I hope you understand, yeah, the transition from here to here. So after this, it is just a matter of regrouping. So if in Kirchhoff current law, we regroup according to the node voltages, in Kirchhoff voltage law, in the node, loop analysis or mesh analysis, we regroup according to the current. So I1 and I2. Okay. So a shortcut, yeah, developing a shortcut from the mesh equation. Draw the mesh currents. Orientation can be arbitrary, but by convention they are defined clockwise. So most of the time, usually we like to draw clockwise the loop direction, yeah, the mesh direction. If you want, you can draw counterclockwise. It doesn't matter. It's also okay. But by convention, normally we define it clockwise. So here I1 is drawn from this node towards this node, toward this node, toward this node, and go back to the original starting node. I2 similarly from this node, going to this node, to this node, and then back to the original node in clockwise direction. So then we now write Kirchhoff voltage law for each of the mesh and apply Ohm's law to replace the voltage by multiplication of the current, of the loop current with the resistor. And each loop follow the passive sign convention. Yeah, as I had mentioned, as I mentioned earlier in the previous slide, you follow the passive sign convention. If it is positive, if it is current entering into the positive terminal of that component, then you know that the value of the voltage is positive. If it is entering negative terminal, then you know the value should be negative. Using loop current reference direction. Okay, so from this, then the loop one, yeah, mesh one can be expressed as negative V1, then plus I1 R1 plus I1 negative I2 multiplied by R2 plus I1 multiplied by R5, right? So here, whenever an element here is shaped by the two loops, right? The R2 is in R2 flows two loop currents, I1 and I2, both have opposite direction. So you have to express this in the Kirchhoff voltage law. Yeah, whenever an element has more than one loop current flowing through it, we compute the net current in the direction of travel. So in the direction of the travel is from top to bottom, then I1 minus I2, because I2 flows from bottom to top. So if we rewrite it according to from the top to bottom, the direction of the loop, then we have to assign negative sign to I2. That's why this one I1 minus I2 multiplied by R2. Okay, then the second loop going from this node, okay, plus V2 plus I2 multiplied by R3 plus I2 multiplied by R4. From here, yeah, the direction of the loop is here. So I2 will be positive, I1 will be negative, right? Because I1 also flows through R2, but in the opposite direction of from the loop direction. So we assign negative sign here. I plus I2 negative I1 multiplied to R2. Okay, so far understand? That will be all for today. So an introduction to the loop and mesh analysis. We will continue tomorrow in the next session to continue with learning some example of using or finding I output using